So today, Yadzan is going to speak about a plague of magnetic spot amongst the hot star of globular clusters. Yadzan is a staff astronomer at ENF Padova, and also part of the talk will be given by Simone Zaggia, who's also a staff astronomer at ENF Padova, and he is as well an author of the paper this talk is based on. So they will be alternating. I'm not sure exactly on the details of that, but they will.
5 minutes.
Fine, they will be alternating, and it's up to them how to do that. So again, please, if you haven't muted your microphone, mute it and switch off your cameras, because that takes the bandwidth that some people get issues with seeing the slides. If you have issues with actually seeing the slide move through the presentation, you can hover on the slide and select pin presentation. Some people have been complaining about the slides not changing for them during the presentation, and that is often because you didn't pin the presentation on your screen. That is the best option. All right, without further ado, take it away, Yadzan.
Okay, thank you very much. Well, first of all, I just want to say very quickly that any reference to the COVID-19 is purely accidental. The title was decided in July 2019. That's when we first submitted the paper. So it took us quite a while also to have it accepted. A summary of the paper will be something very, let's say, old school technology that is stellar variability that has revealed quite an interesting and very unexpected results. Indeed, the paper itself is basically a summary of almost 10 years and presents data that are almost 9 data sets. So I will try to squeeze as much as possible within the talk. I'm sorry for that. The talk also reflects, at least personally, the point of view, the simplistic and naive point of view that at least 10 years ago I had, that one invokes magnetism only when one has no idea what he is talking about, he or she is talking about. So I stand corrected. I'm here to advocate quite the opposite of this. And let's go very quickly. Why would anybody bother and study extended horizontal branch stars, the hot ones? Well, basically, if you're interested in the formation and evolution of low mass stars, that is anything between 0.5 and 2 solar masses, just like our sun, let's say, then you will be most definitely puzzled by the formation of the extreme horizontal branch stars, which are the ones that are here. So basically, we know that stars like our sun will still burn hydrogen in their core for another 5 billion years. And then after that, once it's exhausted the reservoir in its center, the star will start burning hydrogen in the shell that surrounds the core, and will start its ascent along the red giant branch. So in the meanwhile, while it's ascending the red giant branch, the core mass will increase, and the star will get bigger and brighter. All things come to an end, and that is the red giant branch dip when helium ignition is started, and the star just goes all the way down, fainter and slightly bluer. And this is when the horizontal branch phase starts. Now, the real key to understanding why there is so much, why this large distribution in temperature, basically you're going from 5,000 degrees to almost 50,000 degrees, which is quite impressive. And this is basically mostly driven by the fact that although the stars have basically the very same core mass, it is the envelope's thickness that is basically controlling the temperature distribution. So if you returns most of your hydrogen envelope, you will end up cooler around the red clump, let's say. And the more you lose mass along the red giant branch, then you end up hotter stars and reaching 30,000 degrees or 50,000 degrees. So basically the horizontal branch phase is basically almost a thermometer trying to tell you something weird happening that is mass loss along the red giant branch. And put in the word of Castellani and Castellani, in the context of globular clusters, where you have basically the mass at the turnoff is 0.8, you are losing up to 40% of your mass while evolving in the red giant branch. So whatever is happening here is something really peculiar and needs to be understood. So how do you come to lose so much mass along the red giant branch? First of all, let's look at the observational plane, and this is, let's say, the usual Gaia color magnetic diagram of the field, and let's look at the what is called the SDBs, the subdwarf of B type, which are the EHB equivalents in the field. And what you see here is these are the ones basically, and let's say the situation seems quite easy to explain when it comes to the galactic field, the loose galactic field, because the vast majority of the stars in the SDBs basically have one preferential evolutionary channel, which is binarity. So not only 2/3 of them are in binaries, but think of it, half of them at least are in close binaries. So you already have a tan delivered without any trouble. The reason why these stars get to lose so much mass and get over here, because the close binary, the invisible, let's say, companion, will basically suck lots of mass from the SDB star, and the star will get peeled off, and you would see it hotter where it is. There are 20% minority of single stars among the SDB stars, and these are, let's say, are considered to be the byproducts of mergers, which is still interesting as well. Now, what about globular clusters? Globular clusters. So this is His Majesty the King Omega Centauri, which you can see very beautifully has a smooth distribution along the horizontal branch stars from right from the RR Lyrae, 5,000–6,000 degrees, and all the way to 50,000 degrees. And the surprise there is that once you go and target the extreme horizontal branch region, the surprise that binaries are not there. Basically, there is a dearth of binary, and there are, let's say, this thing has been reached. I mean, the conclusion has been reached by many groups, independent groups, that it is almost certain. At the same time, let's say, study by Sara Locatello has already proven that on the red giant branch, the progenitors of those and on the EHBs, basically also the percentage of binaries is still quite low. So there is no surprise, basically, that so far there is only one known EHB binary system among the hundreds that studied so far. So basically, besides the binary fraction difference between the globular cluster's environment and that of the loose galactic field, then add to that, let's say, other differences like age, metallicity, and dynamical evolution. The general idea is that, let's say, all groups would converge on the idea that there is a different scenario, a different path that all stars in these different environments have and use to arrive at the extreme horizontal branch star region. So basically, all roads lead to Rome, and somehow you end up there. And so if it's not binary evolution, what is it? And for example, we will be focusing on this region in particular, the one going from 20 to 30,000 degrees. We will leave aside everything that is called blue horizontal branch stars, because we know that these stars will eventually evolve back and go back to the red giant branch and evolve as AGB, and then Planetary nebulas, and then go back to the white dwarf. We will also, let's say, leave aside whatever is called the blue hook stars, which are stars very hot between 30 and 50,000 degrees, and we will only focus on these. Keep in mind, as I just said, that this region is very, very crowded with many scenarios just explaining how can you end up there. Besides binarity, you have late helium flashers, born-again AGBs, helium enrichment, mergers, rapid rotation, helium mixing. Last but not least is enhanced mass loss. So this is the best view that one would have from, let's say, from a perspective of observational color magnetic diagrams. So you have the mid and near ultraviolet color magnetic diagrams of globular clusters. This is the so-called Milone color plane, in which basically you can see how the distribution along the horizontal branch star is basically is never smooth. So at around 11,000 degrees, there is the Grundle jump, and then there is something called the Momani jump at 20 to 20,000 to 22,000 degrees. And there is another gap as well separating the extreme horizontal branch stars from the blue hook. So this is the best it gets, the best as it gets, and let's go directly to our results. No, sorry. So just a summary of it. So our stars that we are going to target basically have a very precise, very limited range in mass. Same goes for the temperature, extremely thin envelopes. And the most distinctive, let's say, ID is that they are considered chemically peculiar. So stars in this region, as you can see from the jump in here, the photometric jump in here, they are known to show, let's say, chemical peculiarities which are due to diffusion effects. So for example, as Brown has derived, there is an enhancement in iron and other heavy elements that reaches something like between 10 to 20 times the cluster's average metallicity. And at the same time, you would have a helium depletion in these stars that goes to 5 to 10 times the, let's say, the solar value. So they are chemically peculiar by definition. This is an important result to keep in mind. So very quickly, our results. I didn't say this, so we spared the reader the trouble of reading 6, 7, 8 papers, and we decided just to go all in just one paper. So we didn't want to report the ultraviolet monitoring results that we had for one cluster. We waited till we got the second, the third, and then with 3 clusters, you can make some statistics and predictions, as you will see. So basically what we have here is rest in peace VMOS, and then Omega Cam at the VST, and we used Omega Cam for 2 clusters. So basically, we monitored these 3 clusters with in the ultraviolet filter, just to, let's say, to match the maximum flux coming from these hot stars. And what you can see very quickly is that also we recover basically the RR Lyrae and SX Phoenicius pulsational variables, basically in all 3 clusters, but there is the unexpected results of detecting variables in this region for all 3 clusters, which we, let's say, we will report upon now. And just to give you, again, an idea, this is the Grundle jump at 11,000 degrees. This is the Mani jump at 22,000 degrees. And these are 2 instability strips that we know from the study of galactic field SDVs are due to gravity and pressure mode oscillations. So one would say, okay, what's the big fuss in identifying, let's say, variables in this region if you already know that these pressure and gravity mode pulsations are already there? And the answer is quite simply is that when you go study the pressure mode and the gravity mode, their periods are completely different with respect to the ones we found. So pressure mode, which are, let's say, the hotter part, are between 100 and 200 seconds, whereas the G mode are around 2 hours, up to 2 hours. So just to put it very quickly, the G mode are the red ones, and they are, let's say, 2 hours, and these are a few hundred seconds. So as you can see from our definition of extreme horizontal branch stars, we are talking about something between 20 and 30,000 degrees. So we are basically overlapping here. So it is legitimate to ask the question, what's the big fuss? And the answer is quite simply figure number 1, which is we basically report the EHB variables in all 3 clusters. There aren't many, but they are quite effective. And as you can see from the periods reported in each one, you have completely different regime of variability. So 3.3, 5.4 days, 26, 50, and the same kind of, let's say, distribution is also in the other cluster, 11 days, 7 days, 5 days, 19.5, and so on. So it is, pulsation is dismissed very quickly, just simply based on the fact that the period distribution that we have is completely different. It's another regime. Binarity is another thing, but we already said that the literature is on our side saying that it's not binarity. However, we made some effort to try to exclude it, at least for one star, which is, for example, this one, the one at 3.3 days. And please keep in mind, this is a 0.2 magnitude variation amplitude. So it is quite significant. And for this star, we managed to get H alpha flames monitoring covering 3 days, so basically matching the exact period of the star. And at the same time, we took, let's say, a comparison star, an RR Lyrae, which we use, let's say, as just to check the quality of the data. And whereas we do recover radial velocity, significant radial velocity over the RR Lyrae, the situation is quite clear that there are no significant radial velocity variations for the star itself. And when we folded it here, we folded already on the photometric period. So everything is within the uncertainty one would have for, let's say, a single measurement. We repeated the same exercise for 6752, and then once again for pulsational SX Phoenicius, we do have, let's say, variability. We do detect variability of the order of 10 kilometers per second, whereas for the three EHB variables, and this one is I mean, they are within the errors. And moreover, there are at least for another 2 variables that we had that were found in literature monitoring. These were also considered non-variables. So the basic idea is that we can basically dismiss binarity and pulsation. Before going to the exact origin of the let's say mechanism behind the variability, we just report on one last parameter that is of concern, which is basically the frequency of this. So we derive the frequency of EHB variables simply by deriving the ratio with respect to the population that is defined by the color and luminosity of the variables themselves. And as you can see, the values are very much quite similar, so 13, 15, and 12. And if we go and look for these variables in HST diagrams, which is good just to have an idea, because clearly HST diagrams are much cleaner than ground-based, and you re-derived in an inappropriate way, let's say, the fraction of EHB variables, once again, it is still very much, because the HST basically catalogs are very small. So this is another distinctive fact. And when summed up all together, what you have, the summary of the EHB photometric variability is quite impressive. It's periodic single wave between 2 and 50 days. It basically all clusters, and this is a powerful thing. Regardless of the, let's say, the history, the age, the metallicity, helium enhancement potential history of these 3 clusters that we mentioned, basically all clusters, all 3 clusters did show the variability at exactly the same temperature with exactly the same properties. So it is quite a strong prediction. Anywhere you would go, any cluster hosting an EHB population would show most probably the presence of these variables. So if not binarity and pulsation, what is it? And the answer is by exclusion. I hate to say their name, alpha quadrato canum vinatecorum, which is quite simply something, the variability that is afflicting magnetic chemically peculiar B and A type stars, which is quite simply is nothing else than stars that display superficial overabundance of certain chemical elements that form a spot, and as the spot turns around with the stellar rotation, along with the stellar rotation, this induces some photometric variability that one would observe. Now, the interesting thing about once you introduce the word magnetic spot, the idea of magnetic spot, at least for me, the speaker, at the beginning was that, okay, then it is something that is unstable. Whereas when you go and study the literature on these magnetic spots, you would expect them to be quite stable on the order of time scales of decades. Another interesting fact is that, or distinctive, let's say, parameter, is that these magnetic spots are expected to show some kind of antiphasing between their appearance in the far ultraviolet and, let's say, the optical window. And just to show you very quickly, so this is a Kepler light curve of one star, one spotted star. And basically, the 4 light curves are separated by 45 days. So regardless of how complex and detailed features that one would observe, basically, you would see that all four light curves covering basically almost 6 months are very much stable. So whatever the idea of a magnetic spot, this magnetic spot is quite, let's say, persistent feature on these stars. Another interesting thing, the second, let's say, property of them is that regarding the antiphased far ultraviolet and the optical window. And this is seen here by the, let's say, if you look at the flux with considering solar chemical, with a solar chemistry, let's say solar composition, and then you go and, let's say, enhance and do some enhancement in let's see, in these elements, and what you would see and derive the difference between the solar and enhanced fluxes, you would see that it goes negative in here, so you have less flux in the far ultraviolet window around 2000 angstrom, and then when you enter the optical window, it is basically higher in the near ultraviolet. And please look at this here. When you go to, let's say, the red filter, it gets much smaller than relative to the ultraviolet. So this is another distinctive result, distinctive property of magnetic fields. And this paper here by Cantiello et al. Present how do you create a magnetic spot on a main sequence star, which is, let's say, the question itself, because we are making parallel to whatever is happening on B and A type chemically peculiar star. And the interesting thing is that if you focus on this temperature regime, which is our stars, basically 20 to 30,000 degrees, you would soon discover that the envelope in this particular region is still radiative. So you would have a convection zone, the helium second ionization in convection zone just below the surface. And it is, I mean, all this is happening basically in the upper 1 to 2% of the stellar envelope. So this is why at the beginning I said it acts like a thermometer. So you are really seeing something very detailed structure of whatever happening here. So these convective layers are no, let me say it. Okay, so let's focus on this. So how do you create a magnetic spot on a radiative envelope star? And this question has been asked quite interestingly. I mean, the problem is the following. So you can create, you see whatever magnetic spots on the sun, but the sun has a convective envelope. So we understand that. But how do you create it in a radiative envelope star? And this is what colleagues like Ballona and company had, let's say, the trouble of trying to convince people. They came to the point of saying, look, we have 30% of main sequence stars that show spot-induced variability, and yet we cannot understand how do you create the magnetic spot itself. And the answer came, luckily for us, at least, we didn't suffer much, by Cantiello and Braithwaite, 2019, in which basically they explained that the convective elements within the convective cells within these, within the layer itself, basically induce a magnetic field which basically sucks, let's say, the thanks to its pressure, it sucks the photosphere. And so whatever you're seeing here is basically, you get to have a glance of, let's say, the hotter inner regions. This is why it becomes, this region, the magnetic spot will be hotter and brighter, because basically you are really looking at the hotter part. And so just to summarize, the parallelism, at least for myself, when I first tried to connect the two, I was surprised because I didn't know how to put it, because basically you're saying young main sequence stars of 1 or 2 giga-years and let's say up to 7 solar masses would show the same variability of stars that are 0.5 solar masses and 12 giga-years. And so it is okay to be skeptical on bringing this parallelism, but the answer that we had is also, why not? Because there are many other, let's say, similar properties, similar temperatures, same enhancement and depletion patterns, and so on. Very similar, relatively low rotation with respect to their siblings, and let's say both populations, the chemically peculiar stars in here and in here, basically would display a 10% variability among their siblings. Last but not least is the convective core radiative envelope structure. So this is the key element. And this is it. This is what basically changed everything, for at least for our paper, which is to realize that the model of young main sequence stars with let's say temperatures around our the M jump, which is 20 to 30,000 degrees, and you're looking at, let's say, something around 10 solar masses. And if you look at it with respect to a similar model for an EHB star, just like by Swigert et al. 2002, and you would see basically that they are specular, one to the other. And so it is basically this similarity in the envelope structure that basically puts it down that the variability itself may have sense that it is similar in both types of stars. Please keep in mind that also, for example, the Grundle jump that was attributed to the disappearance of convective layers at the surface basically has its equivalents and literature for main sequence stars as well. So there are lots of, let's say, suggestions that the same thing is happening again, also for whatever is happening here. Keep in mind that the convective layers here do not reach surface, basically. There is still one tiny little thin radiative envelope working here. And this was, let's say, the new standpoint that we had. The capability of radiative envelope main sequence stars to dynamo generate magnetic fields can be safely extrapolated to extreme horizontal branch star, which is a strong argument. I mean, we hope it's justified, but it is a strong conclusion as well. And when we put it all together, we try to put all the pieces all together. So at around 20 to 30,000 degrees, basically, you have the onset of magnetic spot variability. We already know that there is the discontinuity in heavy element abundance, as in the work of Brown et al. 2017. And we already know that somewhere along the lines of 20,000 degrees, there is a breaking of a trend of increasing helium abundance trend that somewhere around 22,000 just basically drops down, and everything becomes very, very uncertain in here. So the photometric peculiarities of the M jump and the EHB variability and the spectroscopic anomalies basically can all be explained by the onset of one specific phenomena, which is, let's say, the appearance of magnetic fields. And just very quickly, let's say, do we respect the properties that we anticipated already? So this is a star in 6752 omega cam monitoring over 6 years. The star has a period of 19.5 days. So already this is telling you that with a star with an envelope so thin, there's no way you can say that this is attributed to pulsation or binarity. And so this is the data points of the 6 years put all together, and the model is overplotted as well. So we take the model and compare it to the single stars, to the single data points that are separated year by year. And when we went and checked for phase differences or period differences within the uncertainties, we did not find any. So basically, whatever magnetic spot is, let's say, at play in this on the surface of this star, it is very, very, very stable and persistent, which is quite the opposite of what you expect from, let's say, our background on our sun. The second thing is that let's say, the wavelength dependence that we said before, and this is already, let's say, demonstrated here by this lucky star because it was slightly off center, so less crowded, and we could compare the R magnitude light curves with the U magnitude with the U filter light curves, and you can already see that the amplitude in the near ultraviolet is larger than that in the red filter. So once again, we do respect that. One final check, let's say, consistency test, which is quite impressive as well, is that we know the temperature of these stars, we know their radius, basically from models, and we know their rotation period. So if you take that rotation period, the photometric period, and translate that into rotational rate, what you get is something around 6.1 kilometers per second, which fits perfectly with whatever we've known from, let's say, studies like Per et al., Recio Blanco et al., and so on globular clusters and the galactic field. And as you can see here, this is the EHB stars in this region basically less than whatever is happening around the G jump. So these stars, you would see them, you probably would think that they are fast rotators, but that's relatively speaking because they are not as fast as, let's say, the blue horizontal branch stars. And if we do the final exercise of just switching, trying to translate the 2 to 50 period distribution into rotational velocities, you will get something between 0.4 and 10 kilometers per second. You would think, okay, this is unreliable and so on, but please keep in mind that Ritter, Blanco et al. For at least 2808 found something like there is a non-negligible or significant population of EHB stars that have extremely low rotational velocities. So now I will leave this stand for Simone, who will present one result.
Okay, so why don't we make the modeling of the spots just to have a confirmation that the spots are real. And so we took this 12 EHB 12 that is a pretty isolated but still Gaia confirmed member of 2808, for which we have the best light curves in U and R. And we use the K-Synth software from Montalto, which integrates the total emission from the spotted star and incorporates the full grid of spot properties, so longitude, latitude, dimension, and delta temperature. So the spot, for the spot, we simulated the grid of black body temperature varying between 16,500 and 28,500. So with a delta temperature compared to the 20,500 of the star, temperature of the star. So the contrast ratio between the star spot were derived using the UR filter transmission curves and limb darkening quadratic coefficient from ExoFast routine. And the simulation were repeated, varying the star inclination angle with respect to the line of sight, and of course the best chi-square model from both the U and R light curves were searched, and the best solution with the minimum residual were chosen. And as you can see below, the light curve is perfectly fitted with a star inclination that is 75 degrees, with a latitude of the spot that is 30 degrees, and longitude 50 degrees, and the dimension of the spot is more or less 60 degrees. So 25% of the surface of the star is occupied by the spot. That is a bright spot in this case. And you can see here in comparison with the sun, how it is the dimension of the star and the dimension of the sun. More or less the laser pointer that you see is the dimension of the Earth, so in size. And so you see that while on the sun we have Earth-size dark spots and cool that are short-lived, that live for some days or weeks, and it is insignificant to the sun's luminosity. In this case, we have spots that are 3,000 times bigger than the Earth, and are bright, hot, and are long-lived. And alters the EHB luminosity. Both types, however, are caused by magnetic fields. And this is from the this video is from the ESO press release. So, to what extent this? So, we were, let's say, pleased by the fact that we were able to model these spots, but we wanted to understand why this, if we can explain all the stars in the EHB with spots. And so to what extent the magnetic spots are diffused among the EHB stars. So we simulated the entire population of the EHB stars with spots. So again, we use K-Synth, and we simulated spots with different temperature differences going from 70,000 to 24,000, and we varied the spots luminosity, spots latitude between -90 and +90 in steps of 10, and then the spot angular dimension from 10 to 90 degrees. And then, of course, also the stars photometric periods. We choose 50 periods between 2 and 10 days, and then the star inclination angle between 0 and 90. We generated more or less something like 2 million light curves that were, of course, adding errors, observational errors, like the one that we had with our data sets, and then we extracted every time we extracted a number of results. And of course, we had to filter the light curves with our criteria, acceptance criteria, and already 67% of all the simulated light curves were not recovered due to unfavorable spots properties and observational detection limits, of course. And furthermore, if we assumed that the distribution of the delta temperature spot star are limited, that has a Gaussian distribution, then we are able to find that only 13% of the light curves are recovered. So with this exercise, we found that essentially all the EHB stars are affected by the spots, and so it is a true plug. And so we just found the tip of the iceberg. So going back to Yazan.
Okay, so having granted that the EHB stars are plagued by magnetic spots, one would try to imagine, one would try to figure out what is the configuration of the magnetic field in these stars. And it is exactly what you are not seeing in this plot over here, which are, let's say, the sun and, let's say, other red dwarfs. The magnetic fields in these stars is basically very approximated by a simple central dipole magnetic field whose poles basically are separated by 180 degrees, which you can see here basically. Once again, this is exactly what you're not supposed to see in the EHB stars, because the spots are much bigger. And once again, we draw parallels to whatever is found for the chemically peculiar B and A type stars. And in that case, the use of the so-called oblique rotator model needs to be necessarily off-center from the star. So basically, you have the dipole magnetic field, which is slightly tilted with respect to the rotation of the star. But this is the point. It has to be, the two poles cannot be separated by 180 degrees. They need to, the distance between the two needs to be much closer, which is, for the case of this study over here, they found something around 60 degrees, which is very similar to the star we have studied so far. And so the idea is that with similar studies, this is the incredible thing, the amount of details that one would get if he's studying a lucky star that happens to be very close. And one can do the following results, which is try to simultaneously reproduce the coherency between photometric, magnetic, and spectroscopic modulations, all being single wave. And this is what these incredible guys have done for this chemically peculiar star. Just to show you the first, let's say, coherency between photometric and magnetic modulations. So what's happening here for this star here by Kobzar et al. Basically, as the spot comes in the line of sight of the observer, and the luminosity becomes brighter, basically at the same time, in a coherent manner, the magnetic field is increased, is enhanced. So this already tells you that the magnetism in this star, when it comes into the line of sight, the magnetic spot does induce an increase in the magnetic field overall amplitude. So this is, let's say, step one. Step two would be trying to, let's say, derive spectroscopic information on the properties of these spots. And what happens is that since the two poles are close to each other, basically, and these would not be resolved, basically, thanks to due to the far distance of the studied star, and basically they would define a spot, one spot, and this average spot would basically attract let's say, thanks to the magnetism, it will attract mostly one particular element. So in their case, what they found is that the photometric modulation would correspond also to helium lines determinations, abundances, that are basically all three of them are in coherence with the light modulations themselves. Now, quite interestingly, as the bright spot will come into the line of sight, basically there is another dark spot on the other side, in the opposite side, in the, let's say, antiphased, in which there is basically a concentration of another element, which is in their case, they found silicon. So it is antiphased with respect to helium, and basically here we'll have helium enhancement and silicon depletion, and the opposite on the other side. So this is the amount of details that once you introduce magnetic fields, you really get into. It's scary, and obviously treating with stars at 20,000 light years, just like globular clusters, average globular clusters, you really cannot deal with that, but this is what's happening. And hopefully in the future, something similar could be done for these stars. Okay, so everything else, so far we have only presented result number 1, which is magnetic field. Result number 2, which is surprising, was also dealing with the fact that once you imagine that there are magnetic fields looking at the sun, our closest companion, you would also expect the eruptive side, the violent side of these of the presence of magnetic fields. And these are called the solar flares, which are unprecedented ejections of plasma into the outer space. They release an incredible amount of energy of 10 up to the 32 ergs, and they have a duration of up to, let's say, a few hours. Now, we cannot detect flares on our stars because due to the ground-based observations, you need to have really continuous monitoring and be also very, very lucky in detecting these events because they are, let's say, unpredictable. But thanks to our, let's say, our GTO, our Padova GTO, Omega Cam GTO program, and Mr. Capellaro himself, we basically, in the past 3-4 years, we were granted around 10 hours of observations in service mode, so we could not get the exact monitoring sampling that we imagined. However, we basically the black dots are basically our GTO monitoring with, let's say, better seeing conditions and full width maximum of the stars recovered in NGC 6752, whereas the dust blue data points that you see over here basically are archival data of the same cluster, which is basically used for calibration purposes. So the seeing here of the time of his observation may not have been optimal. However, lucky for us, this one star, this star that shows the the mini burst, basically was falling in 2 different CCDs in the 2 data sets. So this also allowed us to check the consistency between the 2. And as you can see, each data set was reduced separately, and we have a very much consistency between the 2. And clearly there is a particular event, 2 particular events taking place here. So the star would seem to be constant for around 3 years, for around 1,000 days, and then it has this mini burst of reaching 0.05 magnitudes in the ultraviolet filter. Then after which the star basically faints and dims. And at the beginning, well, when we saw this, we saw, okay, some systematics and so on. So we took some time to try to figure out and comparison stars. So these are 2 comparison stars, luckily also blue stars, close to ours, around 20 and 30 arc seconds away. So these are excellent comparison stars. And as you can see, regardless of the dispersion due to their magnitudes, due to their luminosity, these stars do not show neither the drop in luminosity, neither nor the burst itself. So there is a burst that lasts for almost 80 days. And since the first time we saw this happened on, let's say, the 13th of June, which happened to be 2 days ago. We decided to call this star the Padova 1, just a tribute to the patron of the city of Padua. So we go ahead. Thanks again once more. We were extremely lucky to use the Omega Cam GTO time that allowed us to do such observations. So it took us 3-4 years of collecting data, but we report on a very important result. So hopefully Omega Cam will have another life. So we also have, besides the U filter, the R filter light curve of Padova 1, and as you can see, as the star goes into the burst, it went slightly brighter and slightly bluer, reaching almost 0.01 bluer, which is not much. And indeed, the amount of color variations that we get translated into temperature, we get something almost ridiculous of 200 degrees. But anyways, this is what happens. The star comes brighter and bluer, and then fainter and slightly redder. If you have one, there's another and another. And unfortunately, we did not detect the very beginning of this other flare happening in Padova 2. But again, the comparison, it happened 40 days earlier. So it went into the observational gap, the seasonal gap of observations of NGC 6752. So, but again, this is the interesting thing, having the light curves in both the U filter and the R filter. We did estimate the released energy in Padova 1 at least, and we derived something of 10 to the power 40 and 10 to the power 39 in the U and R respectively. So these are extremely powerful events taking place there. Besides these two, we also found other potentially very interesting long-term variables that showed basically only the luminosity transition. And as you can see here, for example, for Padova 6, Padova 7 is quite amazing, because basically if you lose this part here at the first year, basically the star would more or less look quite simply constant and so on. But as you can see, there are some long period variations, and these stars taking place on the order of a few hundred days. And okay, the usual exercise, are they binaries, are they pulsation, and so on. Just very quickly, the idea of binaries in here. So literature would already tell us that binaries is not the answer. However, recently there has been, let's say, new results on extremely low mass pre-white dwarfs and so on, which are very, very close binary systems. The interesting thing about these stars, which are likely, you can think of them as RGB Mankey, so they are binaries, and they cannot, their mass is too low to even ignite helium in the core, so they do not reach the RGB tip, and somehow they end up in the region of the extreme horizontal branch stars. So you expect them to be very, very close binaries, and we did try to check this possibility with Magellan spectrums. We took six spectra of 10 minutes each, one after the other, covering 1 hour. And had it been that this star was Padova 1 was a binary, we would have seen something. However, with the 13 kilometers per second uncertainty that we have, we can only say that it is certainly, I mean, it is most likely not a binary system, a closed binary system. We also checked for pulsation, and once again, this is Padova 1. These two stars are these two stars. So, and in this case, we used, luckily we had a program of UltraCam. So we did very fast photometry, taking 20 seconds for almost 4 hours. And we did check the power spectrum of all these stars, and we didn't find any particular variability in the very short time regime, which is very interesting, because in the meanwhile, there has been quite interesting results regarding the presence of so-called blue large amplitude pulsators, always in the SDB region, which have variability of the order of 20 to 40 minutes. So we certainly can exclude this, and we certainly can exclude also whatever is called high gravity blue large amplitude pulsators, which is another paper that just came quite recently. So if they are not this, what are they? And just checking one last possible scenario, that is, let's say, some exotic stellar evolutionary, let's say, phase. In this case, it would one possibility would have been the so-called late thermal pulses, which is basically a star that is somewhere along its RGB, and while it's going to let's say to the cooling sequence, it reignites helium in a shell, and then somehow it is born again, so it ends up here. And what the thing is, once they end up here, so they are fake stars, fake EHB stars here, but they start their evolution back up to the RGB. So these stars have, let's say, a fast evolution. Indeed, there was one case of the Stingray Nebula in which they found that the star would change 5,000 degrees, change its temperature by 5,000 degrees in only 4 years. So once again, if you compare this to whatever we are seeing in Padova 1, it's 200 Kelvin. It's really 200 Kelvin in over 6 years. So we are too slow. Padova 1 is too slow to be attributable to, let's say, some exotic stellar evolutionary phase. So at the end, so we try to understand what is happening here, and thanks to let's say some digging in the literature, we did find some indication that superflare events can happen in stars, let's say at F-type and B-type, and in such cases, the actual duration of the superflare can be quite significant. In some cases, it was 25 days, and in others, it was tens of days. So and releasing a very similar, very similar energy as our star, as Padova 1 at least. And one final piece of evidence that this whole thing, I mean, this whole phenomenon here that we are looking at is somewhere close to the superflare events, is that the same models by Cantiello et al. That did explain how do you create a magnetic spot do also, let's say, emphasize the presence and occurrence of superflare events. And so, summary, as I said, the EHB does show some photometric variability that was very much unexpected. It is common apparently in all, or at least a strong prediction is that it is present in all globular clusters hosting EHB stars. The variability itself is unlikely due to binarity nor to pulsation, and most likely, very much certainly, is due to rotating magnetic spot. The magnetic spots, the underlying magnetic fields basically should be quite of low amplitude of around 400 GAVs. This I will show later. And basically, these are due to subsurface helium convection zone. And so at the very bottom of it, if you have just to take away of it, the two types of variability that we detect, the violet part and the let's say the stable part, or the double phase manifestations of the magnetic fields, basically come down to one basic conclusion, one strong conclusion, that both of them devise an excellent mass loss mechanism, which is in the absence of binarity that is established, let's say, at least for EHB stars in globular clusters. This could explain how you come to lose so much mass along the evolution on the RGB. So this is the first part of the conclusions that we have. And let's see the bigger picture. This is a nice thing that you always want to say. The bigger picture is one in which not only our results apply for all globular clusters, but we believe, we will argue that the presence of magnetism, although low amplitude magnetism, is also can be extrapolated to whatever is happening to SDP stars. Now, the problem with going and checking this for SDP stars is that, as we said at the very beginning, 2/3 of them are in binaries, and binaries are likely to, let's say, wash away or dominate the presence or the signature of spot-induced variability. So we went into the 20% of apparently single stars, single SDP stars, and we searched for anything that could show spot-induced variability. And we were quite lucky. We found one, which we will consider as our Trojan horse, in which we will invade the territory of SDP region and extrapolate our results there. And as you can see here, thanks to its presence in a test, one test field, the star does show 0.22 days spot-induced modulation. And most luckily for us, it did also flare. Both results were confirmed by an independent study of Bologna. So, I mean, This is already quite telling, because this star itself, this star was studied, the magnetic field of this star has been investigated by 2 independent investigations, and both of them agreed on the fact that the magnetic field strength in this could have only an upper limit of 400 Gauss. So this is only an upper limit, but this is exactly what's happening here. This is telling you, regardless of you see it or not, you detect it or not, the magnetic field is there, and it's inducing and triggering lots of important, let's say, features of this star. And so that was one thing. So we basically, whatever happens for EHBs is probably happening to SDB stars as well. We already brought on the parallelism that we got with we proposed with the young main sequence stars, the chemically peculiar B and A type stars. So what about white dwarfs? And this is another interesting thing. So white dwarfs with hydrogen and helium dominated atmospheres are also fully radiative envelopes. And to our surprise as well, they also show evidence of dark and bright spot-induced variability. And once again, that field, the field of white dwarf studies, has also the problem: how do you explain the presence of magnetic spots in radiative envelope stars? And once again, we use another Trojan horse, which is in this case GD394, and another case in which it had a 12,000 Gauss upper limit of a magnetic field, which is considered extremely low with respect to in the white dwarf context. And basically the variability was quite impressive. You had a 0.25 magnitude in the far ultraviolet. And the basic conclusion by Dupois et al. Was that the AUV variability is basically due to abundance in homogeneities in the atmosphere. And when colleagues like Moaz et al. Would go and try to understand and analyze samples of white dwarfs and so on, trying to understand the variability, especially at these similar temperatures here of our EHB stars, again, depending on what article you read, you have different definitions and different names for the explanation of these spots. So in their case, I think their best scenario, the best model that could explain everything, was non-uniform far ultraviolet line opacity absorption resulting in optical and near-infrared fluorescence. And this is nothing else than basically the wavelength dependence of the magnetic spot being dark in the far ultraviolet and, let's say, bright in the optical region. So basically, it's a flux-free distribution, and this thing happens. So this is again, this is a far ultraviolet light curve. So one last thing regarding the white dwarfs, one would also say, oh, what the hell? The white dwarfs have magnetic fields who have hundreds of millions of Gauss, whereas at best, if you believe us, we are saying the magnetic fields, alleged magnetic fields in the EHB stars are limited to below 400 at best. But the thing is, like, if you compare the two, obviously the absolute numbers are quite scary. But then if you keep in mind the shrinkage and assume the conservation of the magnetic field in the extremely short evolution, because the stars at the EHB region would not go up to the AGB and do all the planetary nebula and so on. They would just simply get slightly brighter and then fade away to the white dwarf graveyard. So the shrinkage factor of 45, a factor of 45 would basically translate, if you have a magnetic field of 400, would basically translate to 800,000 Gauss. So this could also open, and let's say it is quite an important result for the possibility of checking the origin of a magnetic white dwarf, because most likely lots of people would say it's fossil, whereas if our scenario is okay and acceptable, then we are saying that it is due to a particular stellar evolutionary phase due to the subsurface helium-second ionization, which I mean, it opens a new scenario in which for magnetic white dwarfs, you can investigate the possibility that single, very old and low mass stars, how do they, let's say, influence what their impact in their current samples. Last two slides regarding, let's say, the particular impact in globular clusters. So thanks to the seminal works of Graton et al., Carretta et al., we basically arrived at the situation in which Don Carretta has proposed that globular clusters are nothing else than any stellar aggregates showing the sodium-oxygen anticorrelation, which is shown here. So you go and try to understand how can you induce, how can you detect such abundance of variations in both the main sequence and red giant branch stars. And the current situation is that nature beats nurture. So these chemical peculiarities are basically imprinted in the DNA of the stars at their birth. And it's not something that happened along the way of their evolution. There is a long history of, let's say, literature regarding what is the possible scenario for this self-enrichment, and it's not very easy. The search for the so-called polluters is still going on, and at best we don't have a solution explaining the idea that there was population number 1 that polluted population number 2, and so on. So in this context, what does our results would imply? And the answer is quite simple. Surface magnetism, wherever it is origin, taken by the words of Manet, would produce magnetic braking, which anywhere, if you put this in any stellar models, these would provide you with yields that are completely different from any models that do not include magnetic fields. So, and once again, to remind you, magnetic fields, regardless of how low amplitude they are, they would introduce horizontal and vertical certifications. So, and even jets, if you're lucky and get it right in your line of sight. So it is an incredible amount of higher detailed properties that you start to have at hand. And so in the article, basically, we basically wrote this sentence here, so which translated means, what about magnetism in RGB and main sequence stars? It would have been suicidal to try to address all this multiple population issue in that article, so we don't want to go very much there, but we have to, at least in this talk. So the answer, probably, what about magnetism in RGB and main sequence stars in globular clusters? Well, we still don't know much, obviously, but there is a paper by Tom van der Saller, 2017, which basically arrives to our very basic conclusion. That is, magnetic field is ubiquitous on the RGB. They basically went and searched among the Kepler catalog of flaring stars. And as you can see, blue are all stars, and yellow are the main sequence stars that are flaring, and red are the flaring stars. So just to keep in mind that it is even harder to detect magnetic fields on the RGB, because the stars, in the meanwhile, they have inflated dimensions and so on. So any magnetic field will be diluted in a certain sense. And this is exactly what is our conclusion, is that even very low amplitude magnetic fields can trigger some important features, and in this case, flares. And flares are really, let's say, once again, you go into the regime of mass loss and so on. One possible way, I'm just going to cite a few papers that I found recently, in which, let's say, magnetism does induce, let's say, a new standpoint in understanding few issues. And this paper by Caballero Navarro, who basically inferred a direct link between magnetic field and the convective zone in main sequence stars here. So, and what they did was basically, when you do not introduce only magnetism, it comes, let's say, hand in hand with rotation, so it becomes also magnetic braking. And when you do this, they simply managed to do something with only 3 to 4 Gauss magnetic field, which is basically nothing. They managed to reproduce the lithium abundances in both the Pleiades and the Sun, which apparently, I'm not an expert, which apparently is a big result. So as soon as you introduce magnetism via its new phase that is called magnetic braking, something really important happens. And I'm sorry, I'm here only showing, let's say, the latest of clearly many other papers that address the presence of magnetism in models and stellar models and so on. And in this case, for example, for a 1 solar mass stellar model, as soon as you introduce the magnetic field, in this case, they parameterize it with the spot intensity, and the clear impact is that the star becomes less temperature, so it's cooler. So this is clearly has been affirmed in other models, but again, it is important. And if we do this, if we apply this also to whatever's happening in globular clusters, then again, it might make a difference. And once again, on the importance of what does magnetic braking mean if we introduce this. So it is best described in this plot by Van Sanders et al., which basically, as the stars get older, so you have stars with 1 giga-year, 2 giga-year, then you have the sun. Magnetic braking is something, as stars get older, magnetic braking would basically allow you to lose angular momentum, and the star would slow down its rotation. So the periods will get longer. So the plane over here is basically what we think, what should happen if the stars would continue their slowing down, would slow their spinning down. And you would expect that as the star get older, their periods, their rotational period will get much longer. And this is exactly what's happening, what is not happening over here. So they take an astroseismic sample in which they had, let's say, quite accurate ages and rotations. And they do find that there is an incredible divergence in this regime. For ages older than 6 giga-years, something happens. And this is what they call weakened magnetic braking. So something, the imprint of magnetism in field main sequence stars is already telling us something that happens for stars as old as globular clusters. And this is quite important because, for example, already we know that by theoretical predictions by D'Antona et al. And observational evidence by Fabiola Marino et al., that if you go and study young Magellanic Cloud clusters, you do find distinct rotational velocities that are apparently responsible for the appearance of multiple stellar populations. So there's a short step between just including rotation and magnetic fields, and this is what really I think should happen. Again, this thing here would bring about, I would say, as ignorant as I am, some revival in old issues regarding rotational mixing length theory, convective overshooting, and so on. I hope there will be. I think there should be a revival of interest in these long-standing puzzles. And if ever we should take a stand, at least I would think of it this way: that in the context of globular cluster multiple stellar population, nature might deserve a second chance in the forthcoming discussion. Thank you very much, and sorry for the delay.
Excellent. Thank you very much, Yadzan, for this nice talk. Yes. If there are any questions or comments or things you want to say, indicate this in the chat box. So first, Massimo, go ahead.
Yeah,
you can mute yourself and ask the question. Go ahead.
Hi, Yadzan. Thanks and Simone for this great talk. With the LSST, we should find. We already discussed this, a lot of these guys. And on the astrophysical point of view, this should be great because with a continuous survey, we should see a lot of other effects that maybe we do not expect now. I was wondering what is the impact, if any, on the astronomical point of view. For example, if we can use these stars to trace stellar population and the galactic halo assembly history, for example. What do you think?
Okay, so this is a very important point. That, I mean, it was a pain for us when we had to go through the refereeing process, because if we try to compare to whatever happening in the galactic field, it's a mess. I'm sorry, but it's a mess. Starting with the different ages that we are dealing with here, I mean, more or less we are talking about 5 giga-years of SDBs in the galactic field, more or less the average, whereas we are talking about 10 billion years in globular clusters. Add to this the possible difference in metallicities, which is incredible, because as soon as you say there is a huge difference in metallicity between globular clusters, which are second population, low metallicity population with respect to the galactic field, then you're already also heavily impacting on the kind of chemistry and chemical spots that there is that you might expect to find and detect on these stars. So this is a very important point. The other one is that, yes, you can find them clearly in SDB stars, but it will be very difficult because the binarity issue is going to hamper that quite a lot. But clearly, as we exchanged in our emails, LSST is going to be a bummer. I mean, it's going to kill all these, let's say, call it small programs like the ones we were conducting since years, and it took us 4 or 5 years just to come up with one single results. Whereas, let's say, thanks to their hopefully, let's say, continuous monitoring, they're going to blow everything up. I mean, it's going to be an excellent surprise, but we have to look for something new.
400 clusters.
Yeah. I mean, it's
not just 3.
Yeah. Thank you.
Thank you.
All right. Any more questions or comments for Yazan or Simone?
Can I show something in the meanwhile, since nobody's asking?
It has to be very quick.
So,
yes.
Okay, we also managed to add 3 letters, just trying to cite this paper that just came out, let's say, very, when we saw it very late during the proof stage. And these people here, Miller-Bertolami, basically considered this possibility that, as you remember, we would say that the stars along the RGB would trigger ignite helium on the RGB tip, and some the so-called late helium flashers, they will do it while descending the cooling sequence. Some would trigger it here, some would trigger it here, and some would trigger it here. What these guys are saying here, which is very, very interesting, is that once you somehow reach the SDB region, or let's say the EHB, the SDB region and EHB region, there is still the possibility that you still have other helium flashes in the core. Okay, and this is extremely important. We don't know. Most probably, the two things are not connected to one another. I mean, our Padova variables and whatever they are saying here, because they here basically predict that these would show a pulsational properties of the orders a few hours and so on. But if ever, I mean, it would be very, very interesting to try to investigate whatever is happening in the Padova variables that show these strong bursts. Are these strong bursts that last a lot? Are they somehow tracing, thanks to the very thinness of the envelope, some interior process that is happening there? And this is why I still repeat, it's the EHB is an excellent thermometer in seeing these hidden processes that are somewhere there. And only thanks to the thinness of the envelope, we might see something. Again, I'm not sure we are seeing, I don't know, helium core flashes in these stars here, but these loops here are exactly what we have seen in Padova 1 when it did the burst. No, it did it, let's say, very, very, very limited in temperature and magnitude. But again, it could be related to this.
All right. Thank you, Yazan.
Thank you.
I think there are no more questions. Very last chance. Okay, if no more questions,